Welcome. In this chapter, we're going to move on from our propositional logic into what are called predicate logic and what are called quantified statements. So, quantified, sometimes you hear quantity and we think it's a number, and it is going to kind of come down to exactly that. We're going to have quantities of values to talk about. So, 3.1, we're going to do the first instance of this. So, what is a predicate? A predicate is a sentence. And when I say sentence, I'm referring to a logic sentence that contains a finite number of variables. So the variables are finite. The options for each variable could be infinite. Don't get that mixed up. And each statement has specific values are substituted for the variables. So in other words, if I swap them in, I can now say if it's true or false. And the domain is all of the possible variable values. So let's consider this one. P of x is the predicate x squared is bigger than x. And this is for all real numbers. So this P of x, I'm going to take a value like P of 2. What P of 2 really means, again, let me just write this on here for you to kind of visually see. My annotation just went away. Sorry about that. So if I write that down, what does P of 2 really mean? Well, P of 2 is really saying that 2 squared is bigger than 2. And the question is this or true or false? Well, obviously this is 4, that's bigger than 2, so this is true, which means P of 2 is true. So the way to think about that, this is essentially a Boolean function where you're, except the Boolean not in terms of the input, but in terms of the output. So you're going to put a numerical or a string or something, and it's going to give you an output of a Boolean output, true or false. Here, P of 1/2, I'm again going to simply ask the question of P of 1/2 is the same thing as saying 1/2 squared is bigger than 1/2. True or false? False, hopefully. And we continue this process with the next example. And here it's nice and pretty typed out. You can see this. And this is the one where you got to be careful. Again, this is where your math, I'm just going to assume you do this correctly. When you apply exponents, you have to put parentheses around them because it's going to change that to a negative. And so that actually means this is 1/2, 1/4, and this is negative 1/2. So actually this is true. So we're good. So we just did 3 examples of this being true. Of where it's true or false. We can plug in different values. And this gets the idea of predicate logic. So we now ask the question essentially of what is the truth set for that particular P? In other words, when is it? So my domain is all the real numbers for that last example. What portion of all the real numbers is it true? Is it true for all real numbers? Is it true for some of them, one of them, or none of them? It's kind of a thing that we kind of work on, and we have to figure out these different questions. So we are going to, let's look at a different example. Let Q of n be the predicate n is a factor of 8. Find the truth values of n if the domain is n plus. Remember, this is a set of all positive integers. So this is everything 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 forever. Whereas z is a set of all integers. So I want you to pause the video real quick, ask the question, what is the truth set for each of these 2 things? All right. Now, before I go on, if you did that, hopefully you wrote it as a set with the squiggly brackets like we've done before, because it's exactly what we're dealing with. So our first one is 1, 2, 3, 1, 2, 4, and 8, because those are all the positive factors. But when we allow negative integers, we get these ones right here. So in reality, it's important to know what is my domain, because that helps dictate some of the properties that we're dealing with here. So domain is critical to know what are my possible inputs. Now, which of those inputs are going to actually give me trues or falses? That is how we're dealing with this. Okay. I actually did a program recently, and I was using a property that's really cool in Python that automatically does this for certain kinds of tables. So let's look at another example. Let's look at something else we're going to add to, and this is going to be this fancy symbol right here. It looks like an upside down A. This is our universal quantifier. So before I even flip the page to what is universal, when we think, what does that word universal mean? Well, hopefully you're thinking universal means really big, a lot. In fact, universal means everything. So quantifiers, we're going to use some keywords. We're going to use some or all. None is actually a very interesting one. And this is going to be turned out. So if I say X is evenly divisible by 5, like 35 is an example, we want to say, is this true sometimes or always? So this symbol is the universal quantifier. Here are the different ways to actually read that. For every, for each, for any, given any, for all. You see the trend here. It's actually referring to everything that was possibly out there. So because of that, it's an easy fix. So we can simply just always transition it. So let's look at this sentence. Every human being is mortal. I could also say all human beings are mortal, or I can say for all human beings X, X is mortal. This is the logical symbolic form of this. We'll get to even more symbolic, but this is the beginning. But we could also, and this technically would read, so as we technically read, this symbol here is for every human being X, X is mortal. So notice I just created 3 sentences that are all the same thing. You have to be comfortable moving from sentence to sentence in our structures to understand this. This is the same idea for all my programmers out there. You're writing computer programs. You have to understand that you could write this same line of code multiple different ways and it still executes it. It's the same idea right here. We just have to be comfortable with all these different concepts. So let's look at this a little bit further by considering um, what if I say that H is instead of all human beings? Now I can simplify that. Instead of saying all humans H, I can say X within H, then X is mortal for all X. So this is where it becomes kind of the key thing. And now we have this format right here. In fact, I now just need something to replace the mortal part with. For instance, I could now change that. I could actually now add this M of X is really the predicate that the X, M is my predicate. The X is mortal. And if I do that, then I can come up here and I can literally replace this part with M of X. And now my statement looks like for all X and H, M of X. This is where we're going to go because this is the super simplest notation. Let's be honest. All of you, not all of you, but most of you do not like to write words. You like to make stuff as shorthand as possible. We're trying to do that in this formal sense. Now, the truth is, in logic, we do this because we want to simplify things, but sometimes we often use actually words rather than this because sometimes some of these symbols get a little bit mixed up, but you are expected as part of this class to be comfortable with all those different symbols. So let me clear that out for us. So let's do an example. Let's consider D to be the set 1, 2, 3, 4, 5. And consider the statement here, D of X, that's right here. So one way to read this statement out loud. I want you to just think about, you don't need to write that, but just think, how would you read that out loud? And how would you show that it's true? Okay, so hopefully you thought about that. Then for this one, here's a statement, here's again a statement, and here's a question. I want to find a counterexample. That means I want to find an X value that breaks this. So because this is for all, we can easily break for all by just finding one thing. If I say everyone in the class does something and one person doesn't do it, then I'm not telling the truth. So by changing, whenever you use the for all, it's really easy to break because all you got to do is find one thing that breaks it and you're good. Believe it or not, that is sometimes actually really hard to find that one thing, but does exist sometimes. So the first one way to have read that is we could do that for all X and D, X squared is greater than or equal to X. And you can literally just brute force it. Boom, it's done. So we have this, we can work through it. Look at it. A counterexample for the other one is if you pick any number that's a positive fraction, so any number between 0 and 1, not including those two, then this would break down automatically. 1/2 is just one example. You could pick 1/4, 2/5, whatever fraction. All of those, and therefore this whole statement is false. So that's the thing, this whole statement either becomes true or this whole statement becomes false. This is where it becomes really, really fuzzy because sometimes we've been doing little statements. Now we're saying the whole thing is true or the whole thing is false to go from there. So again, that's this symbol. This is the for all. One way I help students remember that is it looks like an A upside down, all upside down. Okay. So there's another symbol that we're going to use a lot of. It's this existential one. It looks like a backwards E. And in fact, I will reference that backwards E kind of shape in just a second. So this symbol means there exists. How do you spell exists? With an E. How do you spell all? With an A. That's a way to kind of remember this. So it's a backwards E kind of symbol because it's existential. And the sentence is there is students in some math class called Math 40 can be written as there exists a person P such that P is a student in Math 140. Or I can say for there exists P inside of big P such that P is a student in this, where P is the set of all people. So this is where I come with a set, essentially my domain that I'm pulling from. And I say, so there's some, now, what do I mean by there exists? I just mean there's at least one. It doesn't have to be more than one. It could be more than one. In fact, it could be everyone. We don't care. Whenever I say there exists, so there exists is actually a much, much weaker statement than for all. For all is super strong because it means everything. There exists, it's not as strong, but it does imply certain things and gives us characteristics. So the domain and both these things are kind of really, really important. And the domain is generally indicated between the symbol, the existential symbol, and the variable name. And so it's normally written something like this: there exists X in D such that Q of X. I have seen the such that part to just be a comma. That does work sometimes. And there's a couple other things, but you can do such that if you have a, or if you really want to be super lazy, if you do S dot T dot, that I've seen that plenty of times in classes. So here's again, let's do an example. Are these statements true or false? So there exists some M inside of the positive real number such that M squared is equal to M. I actually just read it out loud to you. Can you show it's true? Now, can you read this statement down here? I'm not asking you to do it this time. And then here's a question. Can you show that this is false? So hopefully you paused and did that. If you did, the first one is actually pretty straightforward. You can simply click, you can just read through it. We already read through it, but 1 squared is 1. So that's really easy because it's a positive integer. So showing it's true, all I needed to, if I have it there exists, showing it's true, I only have to show one single value. However, to show it's not true, I have to show everything. So wait. I don't know if you're picking up on this. To show for all is true, you have to show everything is true. To show it's not true, I just got to show one thing. However, for there exists, to show it's true, I just need to show one thing. To show it's not true, show it's false, I need to show everything. So in certain situations, it's much easier to show it's true or false. And we leverage that to our advantage in future concepts that we are going to cover, especially in the idea, probably we go on to the idea of proofs. That's a much bigger thing. Okay, so let's talk about some formal and informal language for a little bit here. It is important for us to translate from formal to informal when trying to make sense of mathematical concepts, because while technical terms are really important, you should know them. I mean, just like if you're no matter what your field is, if you're a mathematician, you should be comfortable with both the technical and the non-technical terms. If you're a computer scientist, you have to do the exact same thing. In every field we deal with, we have technical terms and we have things that are just used and we treat them as if they are commonplace. So you need to get to know them. But when you're first doing them, they're pretty foreign. And so it's really good to just translate them back into your layman terms or whatever you're comfortable with. So it's you need to kind of get in this practice of, okay, maybe in my head, I'm going to translate this. And this is, by the way, if any of you have learned a foreign language like Spanish or French or German or Japanese or whatever, often when we first learn these, what our brain does is I hear something in that language, I translate it back into English in my head. I hear it in my head in English. Like this is how I learned. I remember learning French. I learned French for the first time. I'd hear a French statement, my brain would translate it into English. I'd think of what to say back in English, and then I'd have to translate that back into French. The advanced form of speaking French is your brain literally thinks in French. You do not even do the transition. You just translate it. You just understand what that means. So that is two different levels of understanding. So the first time we're doing this, you're getting that translate back to informal, process it, then you pronounce it back into formal, give it up. So let's look at an example real quick. If I wanted you to rewrite these are really formal because they're all fancy statements. How would you write them in non-formal terms without using my two quantifying symbols? Go ahead and pause and figure that out. All right, so let's just walk through these. The first one, for every real number, I can literally say that for every real number, x squared is bigger than or equal to 0. Or all real numbers have non-negative squares. There's lots of ways to frame this. So that is kind of how the first one we really could have done. The second one, again, I could have read this as for every real number, x squared is not equal to -1. Okay. I could have done for all real number. I could have done all real numbers do not have this. There's there's multitude of ways we could have written this. And this is where it gets kind of hard. You're used to one answer for some of these things. It's not always true. Now going back again to see, this is an existential. So what I'm saying here is there's some positive integer so that it's equal to its square. I could have said that, or I could have said at least one. I could have said some positive integer is whose square is equal to itself. Again, there are a multitude of ways to attack this. So we have to kind of take these on and understand them. So let's look at some different ones to go a little bit differently. What about this one says for all integers n, 2n is even? Because notice that the quantifier trails the rest of the sentence. So I'm kind of doing for all integers n, and there exists at least one real number x. So let's just look at this. What's all this one? Well, I can just translate that really, really easy. I can rewrite this instead. So how can I rewrite this? I'm not even doing symbolic. I can literally take this first part and put it right here. And so it says 2n is even for any integer n. I can literally swap that. I can do here x squared is bigger than 0 for some real number x. So that's the idea, that we can kind of move these terms around. So you don't always have them in this format where the quantifier is in the beginning. Be careful of that. You have to look for the quantifier and then rearrange it. All right, so what about this one? How could you write it using quantifiers and variables? Go ahead and pause the video and try doing these things with variables and quantifiers and all sorts of other fun stuff. All right, so hopefully you did that. And if so, let's go through the first one. All triangles have 3 sides. Well, I could have done that. You're going to use, in any case, you should at least use this symbol right here, the for all or universal symbol. Triangle T, for every triangle T, T has 3 sides. I could have done T inside of T and then I have to define what big T is. If you do this, mind you, this latter one for part A, you have to define what big T is. If I did not add the where part of what big T was, this would be invalid because I have no way of knowing what big T is, and therefore I lose some of the properties that we're talking about. So we have to make sure everything is clearly defined. And again, this one against a for all, dog D, and there exists a program P. And we just kind of work through this idea over and over and over again, that we have to figure out how to balance this out and work through it. All right, let's talk about some conditional statements where I have an if and a then. So let's look at this for example. This statement says for all x, if p of x, then q of x. What's that mean? Well, let's look at an actual numerical example. Well, for every real number, this is for all real numbers. If x is bigger than 2, then x squared is bigger than 4. What I'm really saying here, and this is the way to translate this back into English, is if a real number is bigger than 2, then its square is bigger than 4. The square of any real number greater than 2, like all of these are ways to have just simply rewritten that same statement. And notice I could have written it in this nice, pretty format, or I could have written it with all these words. So let's leave this blank right here. I want to write this statement, and then we're going to do these. I'll let you do these two. Let's do the first one. How would I do this first one in this statement up here? Well, notice if a real number is an integer, then it is a rational number. So I have to do something right here. So what's the if part? And if a real number, so the real number is my variable. So I'm going to come up here and I'm going to write in this portion up here, I'm going to x be a real number. And then I said if it's an integer. So that means if x is an integer, then it is a rational number. Okay. So I can do it this way and break it up into those sort of little details. Now, that's because I knew it's a real number. Here, there is no kind of domain given, and so it kind of gets kind of fuzzy. So I want you to pause the video and try B and C. All right, so if you did B and C, you'll get something like these answers right here, which again are for all, and if x is a byte, then x is 8 bits, and if x is a fire truck, then x is not green. Now, these are kind of implicit because the domain's not really given, and so we kind of just infer it. So if it's given, it's not uncommon for us to write this way where we just do for all x and we kind of leave off the thing denoting the domain because it's kind of just given. All right, so let's hit just a little bit more. Let's talk about some equivalence forms of universal and existential statements. In other words, when are they the same? Remember, logically equivalent. So let's take two statements. For all real numbers x, if x is an integer, then x is a rational number. And for any integer x, x is a rational number. These are two statements that actually are the exact same because the set of integers is a subset of all the real numbers. So I already have a real set. We can kind of deal with this. Both have informal translations that all integers are rational. That's really what they're both saying. And that's the critical part. Because the truth is, if x is an integer, well, if x is a real number, if it's really just cutting down to integers, so I can drop the whole real numbers and just say, let's just deal with integers. However, this original statement, there's a funky part here. This one, actually, the statement's true. If I have a real number that's not an integer, but it is rational. That's true here. And it's also true here because, well, not even in this domain. So it's kind of funky. We have two different things. The domain slightly is different on these two situations. All right, so let's look at another example. Let me just go here. How would I write this in two forms? So I have this, all squares are rectangles. How can I write it up here and here? Two forms. So I want this one, I could do square to square, and then x is a rectangle. All right, over here, if x is a square, then x is a rectangle can be my actual in words. And I could simply be making these things a little bit more clear. All right, let's talk about, so these are a couple different things. I'm just going to leave it there for this video because it's already getting pretty long. Play with these things, get to know them. And the biggest thing is, are they still the same? And if so, how can I simply manipulate them to rewrite them a little bit different?